rates of change. Okay. So to do that, we're going to start off with second derivatives. Okay. So we already know from the last class that f prime of x is your first derivative. Okay. Now f double prime of x denotes your second derivative. Okay. And really it's just when you find the derivative of your first derivative. So if you figure out your first derivative, you just find the derivative of that. All right, so let's say for example, if we wanted to find the second derivative, of f of x equals x to the fourth. Okay, so, bless you. First thing you want to do is find your first derivative. Without your first, you don't have your second. Okay, so we know just from the power rule that f prime of x is going to equal, you're going to bring your 4 out to the front, then you're going to subtract 1. Oh, not x, 4 minus 1. Okay, so we know that our f prime of x, or our first derivative, is equal to 4x to the third. And to be honest, after you do a couple of these, you'll be able to just knock those out in seconds. So you don't even have to write that. Okay, so we know that our second derivative is just going to be the derivative of our first derivative. Then the third would be the derivative of the second, the fourth would be the derivative of the third, and so on and so on and so on. Okay, so that means that our second derivative is going to equal the derivative of 4x to the third. So if you get your 4x to the third, write down your coefficient, and then you just find the derivative of x to the third. So you're going to bring down your 3 and subtract 1. Okay, so you just go ahead and multiply those two. So your second derivative, sometimes you'll hear f double prime or something like that, but all the same thing. 4 times 3 is 12, x squared. Okay, so really it's just repeating the same step a second time. All right, any questions on this one? All right. Still writing. Nope, looks like everyone's done. Okay, so what if we wanted to find the second derivative of, oh, thank you, f of x equals x to the 8th. Let me clean that 8 up a little bit. Actually, let me... right, so again, the first thing we have to do is find our first derivative. Okay, so we know f prime of x. Just using the power rule, we're going to bring that 8 down to the front, and then we're going to subtract 1. Okay, so we know our f prime of x is equal to 8x to the 7th. Okay, so our second derivative is just we're going to bring that 7 down to the front, multiply those two, and subtract 1 again. So bring that 7 down, x to the 7 minus 1. Okay, and we'll go ahead and just multiply those two. So our second derivative is equal to 56x to the 6th. All right, so any questions on that one? Okay, so we'll try one more, and then we'll move on. So find the second derivative for f of x equals negative 2x to the 5th. Okay, and I'll give you a minute to try this one before I do it. All right, so for this one, our first derivative is going to equal, just bring your negative 2 out to the front, bring your 5 down, and subtract 1. Okay, so we know our f prime of x is going to equal, go ahead and multiply those two. So we have negative 10x to the 4th. Okay, now we just find the derivative of that one. So our f, double prime of x. There we go. Is going to equal, factor out our negative 10. Derivative of x to the 4th, just bring our 4 down to the front and subtract 1. Okay, go ahead and multiply those two. So our second derivative of x, well, f, is negative 40x to the 3rd. All right, so any questions on that one? All right. Okay, so what if we wanted to find out the actual value of the second derivative? We do pretty much the same thing, but once we solve for the second derivative, we plug in our value. So we'll do one quick example of that one. Okay, so let's say if you wanted to evaluate second derivative at 2. When given the function g of x is equal to 5x to the negative 2. And you want to write it in simplest form. Okay, so the first thing you have to do is find your second derivative. Okay, so we know our first derivative is going to equal, we just factor out our 5, bring down our -2, and subtract 1. Okay, so we know our first derivative is equal to, we can go ahead and just multiply those two together. So we have -10 x to the -3. Okay. And to be honest with me, at least to make sure I don't make a mistake, is whenever I have a negative exponent, I always make sure to put that -1, because sometimes out of habit you may take it to 1, but yes.
Where did the -2 come from? In front of the x.
In front of the, oh, -5. I don't know why I put that there. Thank you. I was thinking of the -2 up there, and for some reason decided to put that there.
No, the -2 got
Nope.
wiped down by.
Oh yeah, it did. I needed that. It really is. And I've been here since 6:45, so it is negative. Yep, that's right. It is -10. Duh. Yeah, that's brought down.
We got them.
Yep, so all we did was apply the power rule there. All right, so now we just apply power rule here. So we factor out our -10, and we bring down our -3, and we subtract 1. Okay, so forgot my second derivative. So our second derivative, go ahead and multiply those two. Finish. So -10 and -3 is +30. X to the -4. Okay, so we have our g prime of x. Okay, well, g double prime of x. So our second derivative of g at 2 is just going to equal 30 times 2 to the -4. Okay. Or even if you wanted to, you could have rewritten this one as 30 over x to the 4th. Okay, so here could have just been 30 over 2 to the 4th. Okay, which ends up being 30 over 16, which reduces to 15 over 8. Okay, and that's your answer right there. All right, any questions on that one? All right. I'll leave that up for a few more seconds. Oops, a set of parentheses around that just because. All right. Now here's when we're going to start using it as a rate of change. Okay. So let's say you have some object moving along a path. Okay, and we track that path and say, okay, the path of that object went along, and normally I like to use dust or a particle floating. Say that path was f of t, where t is time. So at 1 second, the particle was here. At 2 seconds, it was here. At 3 seconds, it was here. So we kind of tracked it that way. So f of t represents the object's position at time t equals whatever. We don't know if it's 1 second, 2 seconds, 3 seconds, half a second, whichever one, but at t equals some time. Okay, so that's why f of t equals the position function. Or it could be s of t, it could be g of t, anything else, but basically the position function is just the actual polynomial. Okay. Now we also know that the first derivative, just by the limit definition of it, is the rate of change, or the instantaneous rate of change as you approach that one spot. So, just rewriting that, we know the rate of change of the position function, or position of the object, is given by f prime of t. Okay, so we know the first derivative is the rate of change. Okay. For this one, v of t will actually equal our f prime of t. And we're going to call that the velocity function. Okay, so we have our position function and we have our velocity function. Oh, bring that down a little bit. All right, so now, just a quick note before I go to the next one. Rate of change is measured in units per unit of time. So let's say in length. Per unit of time. Okay, so for example, you would see the velocity function measured in miles per hour or in meters per second, etc. Okay. So if you're going 55 miles per hour, that's your velocity. Okay, so the one thing we know about velocity is that if you figure out the derivative, and let's do a quick little map here. And let's say you're at a point here and a point there, and you have some graph like that. Okay. Let me smooth this one up a little bit. Okay. So we know that, let's say just for example purposes, at this particular point, let's say you're going 10 miles per hour northeast. Going north, south, west, and east. Okay. Let's say here, if you're going 10 miles per hour southeast. So the direction makes a difference because now you have one direction where you're going positive and one where you're going negative. So we know that it's directional. So velocity has a directional component. Oh, move that up a little bit. Since, let's say, moving at a rate of 10 miles per hour northeast does not equal the rate of 10 miles per hour southeast. Okay, so we know direction matters when you're talking about velocity. Okay, but if we just wanted to know how fast you're going and not take into account direction, so 10 miles per hour northeast, 10 miles per hour southeast, we just want to know how fast, that's when you just find the absolute value of the velocity. And that gives you your speed. Okay, so say if direction is not important, then the absolute value of the velocity gives us, so if we have the absolute value of the velocity, which we know is just the absolute value of the first derivative, that equals our speed, or speed function. All right. Any question on that so far? Okay. Okay, let's add that. Oh, actually, we're going to continue. We have to finish up the next step on this one. Okay, now just to kind of transition. Okay, so we know velocity is equal to the rate of change of an object's position over time t. Okay. Now our acceleration is what they would call the rate of change of the velocity. So if you're going from 5 miles per hour to 60 miles per hour, that's your change in velocity. So that would be your acceleration. So this case, so acceleration is the rate of change of an object's velocity. We'll clean that y up. Over time t. Okay, so if we wanted to know the rate of change of the velocity, then we have to find the rate of change over t with respect to t of v of t, which ends up giving us v prime of t. Okay. Now lining all that up, see a of t, which they usually have for your acceleration, is equal to that v prime of t. Nope. Wrong. Okay, which is equal to our second derivative of our position function. Which makes that our acceleration function. Okay, so to kind of summarize all of this, we know f of t is our position function. We know that our first derivative, which we'll call v of t, is our velocity function. Okay, where we also know that the absolute value of v of t is your speed. Okay, and we know our second derivative. I'll move this over a little bit. Which you know is just the velocity, first derivative of the velocity, and which we'll call a of t is our acceleration function. Okay. All right. Any questions on that so far? No, all right. And our acceleration is measured in units squared. Okay, so for example, if you have meters per second squared, or miles per hour squared, or et cetera, and so on. All right, good ones. Okay, so let's say, for example, let's say a ball is dropped from a height of 64 feet. Okay, so its height above the ground. Oh, actually, that's getting ready to shut off. I might as well